chose me to give this talk today. I'll talk about biomaterials from a metallurgist point of view. I start with my self-introduction. My name is Mohammed Gepreel. I got my bachelor degree in metallurgical engineering from Suez Canal University, and then worked in upgrading metal processing technology in Egypt project in Cairo. Then I got a master's degree from metallurgical engineering department, Cairo University, and then got my PhD from Nagoya University. Then I worked at Nagoya University and then moved to Tokyo University in Japan. In 2010, I joined Egypt-Japan University of Science and Technology, the Department of Material Science and Engineering. I'm one of the co-founders. I promoted from assistant professor, associate, and then full professor in 2019. And that's all in general. Introduced my university is Egypt-Japan University of Science and Technology. It is a university located in Newburgh Al Arab City, Alexandria, in Cairo. In Alexandria, Egypt. It is a partnership between Japanese government and Egyptian government to establish this research-oriented university. It's a special law research-oriented university and governmental one. Basically, we are research-oriented. I mean, many of the students are postgraduate students, master and PhD. We have many scholarships. 5 years ago, we started undergraduate in engineering and other disciplines. I launched a lab of advanced functional metallic material in 2011. These are the current, let me share. Yes, I have the pointer. These are the current graduate students in my lab. As you can see here, we have diverse of research in metallurgy in general. We have laser processing of alloys, Abdel Jalil from Ghana. Nazir about aluminum battery, developing new electrodes for aluminum battery. Some high entropy alloys for high temperature application, nuclear and power plants applications. Charles is titanium base shape memory alloys for biomedical application. Gatsan, phase change material for energy storage. Paul, shape memory alloy iron base for structural application. And Noor is a PhD in using artificial intelligence and developing new biomedical high entropy alloys. Yeah, you can see there are variation in the research topics we are dealing in our lab, and this is some of the facilities is available in our lab. We have electric arc furnace that we can melt under vacuum or inert atmosphere. We can process the alloys by rolling mill. We can have heat treatment furnaces under inert atmosphere or open atmosphere. We have thermal analysis. We have microscopes. We have mechanical testing and so on. And there are many other common testing facilities like high field emission, high resolution transmission electron microscope equipped with EDX, laser confocal microscope, hardness XRD, atomic force, SEM, density ball mill, and many others. So let's go back to this talk. Yeah, biomaterial is a very wide scope topic actually, and I chose one point which is a story of what we are doing in our lab in this field of developing biomaterials. So I chose to show you not from literature, but from our real research output in the field of developing new biomaterials. So we have high concern in designing new titanium alloys for biomedical application. I will show you the progress and the story we are working in this one through around 16 years. We are working in this direction. So the results or the work is presented in this talk today. Part of it has been done, I have to acknowledge, different than our lab. It's Professor Morinaga in Nagoya University, Professor Ninomi in Tokyo University, Professor Hattori in Meiji University, all in Japan, Professor Kobayashi in Japan, and also Professor Nagi Hallam in American University in Cairo, in Egypt, Professor Mona Mar'i from dental faculty of dentistry in Alexandria University in Egypt, and many students are involved in this type of work. So let's go back to the basics of metallurgy or material science and engineering. So the pyramid of metallurgy or material science is composition, processing, so we can have different microstructures, can have different properties or the needed properties to fulfill the performance in a specific application. So this is the story we will work, and we will see today. We start from the composition, from the design, and how to make apply different processing techniques so we can get different microstructures to achieve or to manipulate, to control the properties, to do the function of a specific application. Specifically, we'll talk today about biomaterials, and not all biomaterials. We are talking about metallic biomaterials. It is very common in applications. You can see it in teeth crowding or tooth fixations. So the guides or marks or whatever, all these are metallic biomaterial. The bone plates to heal the fractures, especially the complicated fractures, spinal fixations, and so on, hip joints and knee joints, dental implants, and stents, even many. So this is examples. So actually, this field of biomaterial is very wide and unique interdisciplinary field of work. So if we're talking about the current used biomaterials that used for centuries are developing day by day to meet the requirements and to have less harm on the body after implantation. So there are always the word or the theme of new generation of metallic implants that always under progress, under improvement day by day. So we have to start from the material design, material processing, mechanical property, corrosion testing, in vivo testing, in vitro testing. So in vivo in the lab, in vitro is in animals or in live organisms. So in this sense, cooperation is a must actually. So many people should be involved to have the story reach an successful end. So material engineering or metallurgist, scientist, chemist, biologist, surgeons, all should cooperate to have a success at the end. So a general problem for biomaterial is it should fulfill basic requirements. So not any alloy that can be working in biomedical field actually. First, it should have successful biological needs and requirements. So the material should contain non-toxic or allergic elements like nickel, vanadium, cobalt, and so on, as we will see. And also it should pass the in vitro and the in vivo assessment. So this is biological, this is a special characteristic for the biomaterials, other than other functionality, that's mechanical functionality or chemical inertness and so on. So mechanical functionality like high strength or high or long fatigue life, or some other mechanical properties like low Young's modulus, sometimes it is very essential. Sometimes very high Young's modulus is also essential, needed, depends on the application. Also, ultimate wear resistance to do the function. Another one is the chemical needs, like we should show low corrosion rate because of the complication that may result by if the material are corroded after implantation. Also, there may be some other modification like making side layers or surface modification to prevent the ion release and so on. So let's imagine a biomaterial, this is in the left, has been implanted in a body, okay? And there are adjacent tissues, and this is the bone, the neighbor bone that's the implants has been inserted in the body. Let's see how the body interacts with the biomaterial. This is length scale. This is time scale. After 1 second, which in the very, very adjacent to the biomaterial or the implants that has been implanted, you can see there are very fine debris or ion release. Okay, just 1 second. Within days, these debris or ions are released from the biomaterial or the implant. They will interact with the cells around adjacent to the biomaterial. And then with days going and more depth, the interaction is there and the effect is there. So at the end, the bone will heal and grow or not. So the interaction between the biomaterial and the cells, live cells, and the bones and so on is happening in short time, and we should consider the interaction. So not any material can be used for to be implanted in a body. We made a review to show you the importance of how can we classify different elements about its probability or possibility or compatibility to be used for manufacturing biomaterial or implant. Here, a table, we summarized different elements, how different interaction with the cells, how it will go, like biocompatibility or carcinogenic or genotoxic, mutagenic, cytotoxic, allergic, corrosivity, and so on. So we classified the elements to good elements or compatible, like green one, as you can see here. So titanium are green. So you can see it's very good. Titanium is very good one. Zirconium is very good one. Niobium, rubidium, tantalum, and so on. Molybdenum. Some elements has good issues, which is the red, the green, and bad, which is not proper, which is red colors, as you can see here. So here we can see some of the elements are in between. So maybe used, maybe not, depending on the application and so on. But some other elements are very harmful in all cases, like vanadium, chromium, nickel, cobalt. So as you can see, or red. So all carcinogenic, allergic, and so on. If we go back to the most common biomedical alloys in the field, the worldwide, you can see titanium 6 aluminum 4 vanadium alloy. That's we call titanium 6,4. It's very common to manufacture most of the implants. Okay, it contains anabolimum, contains vanadium. We said here vanadium is prohibited. Okay, so it's a big problem that it contains vanadium. So we should have vanadium free. Although it is currently worldwide the most common used alloy for implant manufacturing. Cobalt, chrome, molybdenum, also very common in some applications, as again, cobalt and chrome, as you can see here, classified in this way. Stainless steel, that contains its iron base, nickel, and chrome. So nickel here again, and chrome here is again. Okay, so all what is most common by medical alloys has a troubles for long-term implantation. So they will release some toxic, allergic, or carcinogenic elements. So they should be avoided in future. Okay, even in the short term, we can see some alloys compared to other alloys, how the bone will interact. Does the cell find the place very nice to grow easily, or it has a limitation and it has a bad impact on the cell growth, new cell, and the healing process? Here is an example of the bone plate after implantation. One alloy that's called TNTZ, titanium, niobium, tantalum, zirconium, which is good. All elements are very good. Compared to stainless steel, which contains nickel and chrome, you can see here the new bones are growing here. The new bone are growing, but compared to stainless steel, is not growing. So this means that the environment are very healthy around the TNTZ, which is titanium, niobium, tantalum, zirconium alloys, compared to the alloy that contain nickel and chrome. So again, the growth of the bone or the new bone is the function of the alloy and the alloy composition. Okay, so if we go back to the other properties needed for biomedical alloys, so some mechanical properties are needed to fulfill the application. So different application, different requirements. So sometimes or majority needs high strength, a high fatigue resistance, and one of the important things that we will show you today is low elastic modulus. that because the bone itself, the God created it very elastic, very elastic. So if the alloy that will replace bone is not elastic with good elasticity enough, is matching with that of bone, there are a phenomenon called stress shielding. So there are mismatch in the elastic property. So a big problem happens after implantation. And most of the surgeons know this problem, that after implantation, the bone itself loses its density and become loosening of the implant, and we have to make revision surgery and very many complications. So superelasticity or elasticity is very important in many of the applications. Also, some of the applications like stent, we need low elasticity or high stiffness in some of the stents and so on. So in a way, we have to engineer the property depending on the applications. So I'm showing here what does it mean stress shielding. Stress shielding is this is the body, okay, that this is the bone skeleton. And if you replace the hip joint with artificial hip, okay, if there are the load go through from the body, go through the artificial hip to the stem. So if there are mismatch in the elastic modulus, there are many problems here. These bones doesn't feel the stress, so it fails. So if we compare now the commercial alloys that used already in the market worldwide and compare it to the elastic modulus of the bone, okay, you can see here, this is the most common stainless steel or titanium 64 or cobalt chrome and some other minor alloys that used in biomedical field. Compared to that of bone, you see the bone elastic modulus is very small, very high elastic, but compared to the all commercial, so the stress shielding is a big problem. So last 20 years or more than 20 years, there are a big say to introduce new alloys with low Young's modulus to avoid this stress shielding, which is a big or one of the main reasons for the failure of the implants or biomaterials after implantation. Okay, so fortunately, there are one alloy, nickel or titanium nickel alloy, that has very high or very good elastic property. Many people has started to use titanium nickel alloy because of this good elasticity compared to that of titanium 6 aluminum 4 vanadium. Okay, 6 aluminum 4 vanadium elasticity is not good, but also vanadium aluminum also are toxic elements. So we should solve these problems. If we go back to another trend came to replace this alloy with titanium nickel alloys, but we have high nickel content. Nickel itself actually also has a problem. Its nickel is cytotoxic and cause allergy for many of the people, for many of the men, many of the women. As I remember, around 20% of the men has nickel allergy. I'm one of them. 10% of the ladies has a nickel allergy. Okay, so we have to avoid allergic reaction. So this means the failure of the implant after implantation. So many research goes to the reduction of elastic modulus of the alloys. We have to introduce new alloys with low elastic modulus, and from the beginning we have to avoid these elements that makes troubles, cytotoxicity or carcinogenic or allergic and so on. Okay, so I will not go deep about what people did, but I will show you roughly what we have done actually. So titanium alloys, the beta type of titanium alloys is one of the solutions. Titanium is an element, as you know, it's active element that has allotropic transformation. It has alpha phase at room temperature with HCP and beta phase with BCC at high temperature. There are transition from beta to alpha that we call beta transes. If we add elements to change this beta transes temperature, if it increase the beta phase zone, we say beta stabilizer. If it is increase the alpha zone, we call alpha stabilizers. If it doesn't affect, like what we call it neutral elements, like tin and zinc, zirconium. Okay, so alpha stabilizers like aluminum, oxygen, nitrogen, carbon. Beta stabilizers that stabilize beta phase to room temperature, to a wider temperature range, like vanadium, molybdenum, tantalum, and so on. Anyway, so to engineer the microstructure or the phase stability of the alloys is very important because it is a function of the property itself, actually. As we can see here, so there are, yes, this is a schematic showing how the researcher tried to develop new alloys for implant applications. That's beta type titanium alloys and aluminum and vanadium free. This is the key search in the Scopus. Actually, it has been done in this time range. You can see that beta titanium alloys and aluminum and vanadium free is increasing so because it is a solution. Yes, so many people has worked in developing beta type titanium alloys. That's good, excellent biological biocompatibility and high strength, high fatigue resistance, and low Young's modulus. So this is one of some of the targets to as a new generation of biomedical alloy that solve the problem. Here we are summarizing the different alloys used commercially from 1950 to 1990. All these alloys were used commercially, actually. And all these types has this Young's modulus, which is around 100, 110 or something, okay? And it, unfortunately, compared to the bone, the elastic modulus of the bone is high. And also the next generation, which starts from 1990, to say beta type titanium alloys can do or solve the problem that we have to avoid the toxic elements like vanadium, aluminum, and so on. And we substitute with niobium, zirconium, tantalum, and so on. Okay, and we have lower Young's modulus. So now we solved the problem. They solved the problem partially. So the elastic modulus is much better or lower than first generation, and all are beta type, and they avoid the toxic elements and so on. So we developed some technique to further improve or to manipulate the phase stability with some diagram that we have developed in 24 that we call it phase diagram of bond order metal d orbital energy level. So in this diagram, I won't go about details. This is electronic parameters we are using to design the alloy. In this diagram, we can easily predict the phases of the alloy as a function of the composition. So we do these calculations, and we can predict from the beginning how to design alloy for biomedical with a specific phases. It's from the composition point of view, and also how to achieve low Young's modulus in this phase diagram. So low Young's modulus can be achieved in this diagram around this one. So this values is the Young's modulus and so on. Okay, so in some way, this as a function of the phases, Young's modulus change with the beta stabilizing elements content. You can see here different phases show different Young's modulus, as you can see. But most of the elements do the same geometry, actually, of how the phases changes, how it is related to the Young's modulus. Among all these, we can see that the lowest Young's modulus, which is one of the target, is around the single beta phase zone with beta plus omega and other phases around it. Okay, so if we catch this point from the composition point of view, we will achieve the lowest Young's modulus. So the highest elasticity, which is lowest stress shielding probability, and so on. Actually, alhamdulillah, we did some work in this, and we can see some of the alloys that we have developed based on these theories, titanium, zirconium, niobium, tantalum, and with some minor modification with iron and oxygen. So we can achieve Young's modulus very, very small. We can achieve very low Young's modulus, very close to that of bone. The bone is in this range, okay? And we can achieve this one. So how can we do it? And by composition, as you said, and processing, cold rolling, and followed by solution treatment. So these conditions is a material processing with a composition, so we can achieve the required properties. And this is the strength of these alloys, is acceptable compared to the commercial alloys and so on. not only mechanical property, we should measure how these alloys will behave in simulated body fluid. Yes, we should measure the corrosion resistance, also the cell viability, how the cells, especially the bone cells or live cells, different live cells, depending on the application, will react with these bones. So all are successful. That's the cell are very live, active, and so on, and healthy. Okay, this one has been published. Okay, so here it's very good thing actually. It's out of the collaboration with many people. We developed one alloy that's very good and proper for stent application. You know, stent is a setup that's used to widen the vein or artery when if some narrowing happening there. So the blood can go and flow freely. We have developed an alloy that's can be used to develop or to design new type of stent. That's we call it self-expandable stent. So that's located there at the vein or artery with that has a problem, and then it is by itself expands. Not only this, actually, the material itself is very unique, but also we did some surface functionality. So we create nanotubes on the surface of the stent itself. And these nanotubes, as you can see here, this scale is 200 nanometers. So these tubes is around 30, 40, 50 nanometer in width, okay, diameter. So in these tubes, we can fill it with the needed drug, actually. And after implantation, these drugs are released. So to make local treatment of the operation of the affected place, actually. And this is, we have filed the patent, and it was granted in May 2020. We have cooperated here with material, chemist, pharmacy, and textile for the design of the stent itself, and so on. So there are many people should cooperate. Okay, let's move. If we say that a super elastic or elastic, high elasticity material is very important in biomedical field, especially stent or dental application for teeth crowding. This wire should be a very high elastic one. So we developed another alloy that's very high elastic. Means high elastic, this is a stress strain curve, right? If we stress the material and reload the material, how much strain it is recovered, how much strain is permanent, okay? You can see this is, we do cyclic. We load and deload the material, the alloy, load, deload, and see how much strain is recoverable, that can be recovered. So we can see that the material or the alloy, that we call it super elastic alloy for stent and wires production, by training the alloy, actually, we can achieve higher elasticity, very high elasticity, you can see, okay? By training, this is the 12 cycle, we can train them at the alloy, so we can have much higher elastic strain, okay? So if we compare different alloys or different cycles, we can see that this is the stress strain curve, loading, deloading, loading, deloading, loading, deloading, okay, and so on. Different alloys, okay? The alloy can recover up to around 9% strain. This is a huge strain is recovered, okay? So this is very important to design an alloy for spinal fixation. There's the spine. You need very elastic one. And for these teeth crowding wires and for the self-expandable stent and for dental tools and for endoscopes, for all this needs very high elastic material with good strength. So this is achievable by this alloy design techniques, okay? So all these applications are very important to be very elastic, that can go flexibly and do its function and so on, okay? And we have to develop different alloys and so on. Another properties needed for different stent that's called balloon expandable stent. So this is the different type of stents, also needs different properties. I will not go in this one. Okay, anyway, so now we say that's very clear that the story that to develop new alloys for that doesn't contain toxic or allergic elements and do the function, very mechanical function, biological function, chemical function very well. However, actually, as you can see here, most of the alloys that we have developed are containing these elements, niobium, tantalum, and these are very expensive elements, actually. Tantalum is very expensive. Vanadium is very expensive. And we should avoid vanadium. Tantalum is okay. Niobium, very expensive compared to titanium. This is the price per kilogram, actually. Okay, so we did another work to, if we know the story, the way, the mechanism, the technique, that if we control the stability of the phases and the microstructure, we can achieve the required properties. So we did it using the high cost.
Sorry, Dr. Gepreel, we have those sound. Can you hear us? Or?
850 and solution treated and so on. So the properties as we are planned, strength is very good.
We have lost the sound 2 minutes ago.
Sorry?
We have lost the sound 2 minutes ago.
So can I go back?
One slide.
This one?
Yes.
If you like, we can give a few minutes or for anyone to comment so we can continue later. Or shall I continue?
Can continue.
Okay. So again, as I mentioned, that it is successful. It is successful to have alloys that fulfill the requirements, but the problem is the cost, because most of the alloys that recently developed contain high amount of tantalum or niobium or molybdenum and so on, and the price of the elements itself, as you can see, is very high compared to titanium and others. So the idea came that how can we achieve new alloys that containing these low cost elements and in the same time achieve the same properties needed for bioimplants applications, as we have successfully did in last time. Okay, so this is a research that we are working maybe 15 years ago in this field. If we use the same techniques, the same mechanism, using the BOMD diagram, so we can predict from the composition the phases. Okay, this is the alloy that's function of iron, is cheap elements. Okay, and small amounts of the expensive elements, very small amounts. So we can control the phases and the microstructure by the cheap elements, and while these high cost elements is minimum, and to do the needed function and so on. According to our prediction here, from the composition point of view, so these alloys 4 and 5 are promising to show the needed low elastic modulus and so on. As expected and as planned from the composition, this is experimental. So as function of iron content in this alloy system, yes, this composition will show phase stability transition from beta phase to beta plus martensites. And the lowest elastic modulus is achievable at this composition. This is at 5 iron. Okay, so now, yes, the tool is working very efficient from the composition. We can manipulate the microstructure. We can control the properties that we need, and the low Young's modulus is achievable. And the strength is still very high for these alloys has been developed, actually. And this is very good work actually have been done. This was a very promising alloy we have developed, which is cheap and successful for all tests, biological tests and mechanical tests that's needed. So we have moved to for this alloy for animal tests, actually, because it's successful in the lab. So we go for animal tests. This is a tibia of a rabbit, and a column of the alloy has been implanted in the tibia for around 60 weeks, and for 6 months, as we can see here. So this is the implant. After 6 months, we slaughter the rabbit and see how the bone interact with the implant itself of the alloy. If we compare our alloy, that's this one, which was successful, it's a 533 alloy, compared to the commercial, say, titanium 6, aluminum 4, vanadium, and stainless steel, that is a commercial one. We can see here our the bone. Yeah, this is the implant, and this is the bone, new bone generated around the implant. We can see here, it's very nice. The bone grown around the implants very nicely, very good, and very good adhesion between the bone and the implant is much better than titanium 6-4. And you can see here the bone doesn't grow well around the stainless steel implant and so on if we compare it. So this means that this alloy is very successful from composition, cost, biological property, mechanical property, in vivo, in vitro tests point of view. It's very successful. Okay, so we can also further work in reducing the cost by many techniques. Okay, I will not go in this one, but anyway, we can calculate the density and everything. And we can see here also the cells for some new alloys that we have developed, low-cost alloys, compared to the titanium 6-4. We can see after implantation, this is bone cell. After implantation for 6 hours, we can see in only 6 hours, you can see the cell, if it is around on the surface of our alloys, compared to that cells on the surface of titanium 6-4. You see the cell here, number is less. The cell itself is very thin. You know, it is weak cell. So the cell is dying, but the cell in our alloys, over our alloys, is very healthy. Number is increasing and so on. So the new alloys we are doing, so the bone cell itself is very healthy, accumulated and growing much faster than and healthy than compared to the titanium 6-4 alloy and so on. Okay, not only this, but also we go about some other mechanical properties like tensile strength and specific strength and so on. We could achieve from this alloy system, titanium 14 manganese alloy system. It was very successful in mechanical property, biological property, and strengths we could achieve by some thermomechanical processing with very high strength, actually. And with this low density compared to stainless steel and so on, the specific strength of the alloy is very high, actually. And the cost is very low cost, very high strength, very high specific strength, very good properties compared to titanium 6-4 and stainless steel and so on. Okay, so this is summary. Not only this, but also we can do some surface functionalization for dental implants, actually. We can, some of the applications for the dental implant, for the tooth root, to have very good surface suitability because of it is needed for a dental. So this is also in cooperation with dentist. Magid and Rahaf are dentist, and Professor Mona is dentist, and so on. So we make even the surface functionalization of the implant itself with some bioglass. So we can achieve very super hydrophilic surface of the implant itself. And this is actually filed the patent and so on. Recently also, we use artificial intelligence to assess or to speed up the alloy design. Now we have very good understanding, the relation between composition, processing, properties, relationships. So we can speed up the discovery of new alloys for biomedical field. So we use neural network to the design of new titanium-based alloys for implants with low Young's modulus and high biocompatibility and so on. And we are very successful in this, actually. So to go for concluding remark, many excellent titanium alloys has been recently developed, showing a very competing compatibility compared to the commercial one for different biomedical applications. It showed high strength, low Young's modulus, high corrosion resistance, easy processing, low cost, good biocompatibility. However, we need further in vivo and in vitro tests that need to so implants or biomaterial to be developed. It takes minimum 15 years of work, and we should go for the next step. It is successful now in the lab, and we should go further for the in vivo and in vitro tests, so we can reach to the clinical trials for official approval. Official approval is very complicated issue actually, and so we can compete the commercial materials. So in this sense, cooperation is a must. We need to cooperate with all concerned specialties. So our new alloy that we are producing or developing can reach to the target patient healthy and very successfully and for long-term implantation. I thank you so much for giving me this opportunity, and thank you. I think now I am ready for receiving any comments or questions. Hello?
Dr. Mohammed, I have a question about the future of biomaterial.
Actually, is one one of the very fast-growing discipline actually, because many companies are working, and it's actually they get very good money actually. But the important is to have quality. The field is very open, very wide scope, and the important is to have something valuable, so we can compete what is already in the market there.
Okay, thank you, Dr. Mohammed.
Sra?
Yeah, so my question is, how can someone with an engineering background get a better understanding of the biological tests performed on biomaterials?
We do it. It is learnable. We can do it. All our students are engineering background. Some of them are material. Material is better or easier for them to treat biomaterial. But we have also mechanical engineering. They do it, but at the end, actually, we don't need to do everything by yourself. But at least, as I said, that this type of field is multidisciplinary, interdisciplinary. So we should have a team. So we should have collaborators. So this is what we always do. You can do, but it's better to leave it for the expert in this point. So he will do it much better. And if you cannot do it by yourself, it can be. It doesn't take much. For example, actually, the artificial neural network that we used in the alloy design, it takes from the student only 1 month to know the need, and he can achieve very good results. Alhamdulillah, we have one patent and one program. We are filing for intellectual property. So I mean that good engineer can do it, no problem.
Okay, thank you so much.
You're welcome. I'm afraid that the content of the talk was very deep for you. So no more comments?
I think there's no, but how if anyone wants to reach you, Professor Mohammed?
Yeah, through my email and WhatsApp, or even by phone, no problem.
Thank you.
So if no more comments, we can conclude now.
I think we can finish it now.
Yes, thank you so much.